Hello, I think we can start. Welcome everybody to my talk. The today's topic is demystifying process address space, heap, stack, and beyond. Some agenda. First, there will be some short introduction. Then I will talk about the theory of process memory layout and operating systems. And at the end, we will just analyze some process on Linux, some practical example. There will be time for questions at the end of the talk, but if I say something incorrect or something wrong, feel free to interrupt me. I'm sure there are a lot of people here who may know more about this topic than me. My name is Piotr Wierciński. I work at the Qt company in Norway here in Oslo. I work for the WebAssembly platform team, which is the newest platform we support in the Qt. And in my free time, I'm just trying to understand how computer and life works, and I think that's 99% of who I am. Here are my socials. I don't really post much, if anything, but in this presentation I will have a lot of links and references to external resources. So if you want to click those links and follow them, you may need slides. And the QR code will just take you to the PDF with slides. Okay, so let's just define what this talk is about. Given a very simple scenario, we have a program, a binary, let's assume in ELF format, and we have an operating system. And when the operating system starts a program, it creates a process in the memory. And a process is just an instance of a running program. And this process has a very specific structure and very specific layout in the memory. And this is the topic of entire talk. So before I started diving into this topic, I had a very simple mental model, which was mainly enough, but I feel like it's lacking a little bit. So if this is a process layout space, I was thinking, okay, we have a program which has instructions that we execute on CPU. So we must have a code section somewhere, probably at the bottom. Then we have the data sections. For example, we have the heap, we have the stack, and I've been always told that the stack is at the top and it's grown downwards for some reason. So I guess stack is at the top. Then if we have the stack, we must have the heap. And there is not much space left for the heap, so I guess it's somewhere in the middle. And if we think more about it, then we also have some third-party libraries. Like we have std library, we have some other frameworks that we use, so I guess they must occupy some free space, because we need to have them in our other space in order to call their functions. If we refer to the function by pointer or something, we need to have this pointer accessible in our memory process space. And a short disclaimer. Do I need to know all this as a software engineer? I think the answer is very simple. I think if you are not working on Linux kernel, on operating system, and even then you probably don't need to know this. So if you don't know this or are not interested in this, please don't feel guilty. It's not gonna change your job. It's just interesting to know, that's what I believe. But if you just want to rely on simple models, it's not an obligation to know all these details. This talk will be mainly about the implementation details of operating systems, pretty much. So we talk about the memory. And when we think about the memory in terms of the computer, there are basically two ways we can think about memory. We can take the blue pill and get the very comforting illusion of virtual memory, which is just abstraction created for us programmers. Or we can take the red pill and we can see the memory, the physical memory, where the pointer, actually the address, designates the physical location somewhere on the hardware. If we take the blue pill and we look into the virtual memory illusion, we have a very nice and comforting illusion of having continuous block of memory without any gaps. The entire process space is available for our process. It's a virtual memory, so it's just a model. It can be actually bigger. The space can be bigger than the physical memory that is available to the device, and we are isolated from other processes. We cannot see the memory of other processes unless we use some inter-process communication explicitly. If we take the red pill, it looks more like this. This is the physical memory reality, and each color represents single process. So this memory has a very strict hierarchy, and each level in hierarchy differs from the next one by orders of magnitude in terms of like memory access. This memory is also fragmented. Our program doesn't occupy the continuous space. There's no isolation between the processes. Sometimes you can move physically one byte higher or lower and you will meet the memory of other process. and part of this memory is specialized. For example, the L1 cache. The CPU has a couple of caches, usually 3, L1, L2, L3, and the L1 cache is split into instruction part and data part. Because normally in RAM or hard drive, we just store the program and the data together. But on the L1 cache size, on the L1 cache level, we have one part of cache strictly designed for the storing the data and one part strictly designed for storing instruction. And this has a fancy name of modified hardware architecture, which has nothing to do with hardware, by the way, but that's how it's called. I can actually check on my system by using the command lscpu, which will show me information about my CPU. And if I look at the caches, I can see that the cache L1 is split into the D part and the I part, it's data and instruction. Okay, going back, we have this mapping between virtual and physical memory. So virtual memory is continuous, but those parts of virtual memory, those chunks, which usually have a fixed size because those are called pages, virtual pages, they are mapped to physical memory. And they can be mapped to the physical memory, the RAM, they can be mapped to the hard drive. So it's important to understand that if we move one page, 1 kilobyte or 1 byte higher or lower, and we go through the page boundary, this new page can be mapped into totally different physical location. And if it's not available in the primary memory, then we catch the page fault, then we need to load the page from the hard drive. Okay, so some disclaimers. A lot of things I'll be talking is very dependent on the architecture, and in this talk I will focus on x86 architecture. I will be talking about virtual memory perspective, but I think it's important to remember that there's a physical layer beneath it. I will focus on Linux, and maybe I will use GDB with some plugins. So if I run GDB and it looks unfamiliar, don't get confused. It's just like a plugin that you could download to GDB, because GDB is exposing a Python API. So there are a lot of plugins to make the GDB more convenient to work with. Okay, so how big is this process address space? And we are focusing on the virtual address space on x86. So in case for 32 bits, we have naturally 2 to the power of 32 bytes, which is 4 gigabytes. And in case of 64 bits, we have naturally not 2 to the power of 64. We have either 2 to the power of 48 or 2 to the power of 57 bytes, which gives us respectively 256 terabytes or 4 petabytes. Okay, so when I saw this, I think the natural question is, why are we not using 2 to the power of 64 on 64-bit? That seems like a natural choice, right? And this limit, 2 to the power of 64, is still a theoretical limit of architecture. So the registers are not 48 long, they are 64-bit long. But the 48 and 57 bits is just what current implementations are supporting for practical reasons. And by implementation, I mean combination of both the hardware and the software, which is operating system. So 48-bit addressing is pretty much a default in modern computing. It has been introduced by AMD in 2003, so more than 20 years ago. It was the first 64-bit CPU in x86 family. And yet 256 terabytes is quite a lot of memory. It was enough back then and still is. So on most computers, we have 256 terabytes using 48 bits addressing. And then 57 bits of addressing is just introduced by Intel for some specialized servers, which require more than 256 terabytes of memory. And it actually is supported by current operating system, like Linux merged the patch in 2017. And Windows Server editions also support 57 bits addressing. But the key takeaways are that in 42-bit architecture, we use 42 bits for addressing. In 64-bit architecture, we use 48 bits for addressing. If I go back to this listing of a CPU and scroll up, I can see the address size on my machine, which is 48 bits virtual. So yeah, this is the default pretty much. Here's some further reading, if you are interested, and we can move to this. So this process address space, we know how big it is. So how it is organized at the top level. So at the top level, it's divided into 2 parts, the kernel space and the user space. The user space just contains the program that we are running, so our program. And the kernel space just contains the operating system kernel. And the switch between this happens whenever we are calling the system call. So our program runs in user mode, but then when we are calling some system call for input-output operation or for some other stuff, then we switch to the kernel mode, which switches the hardware mode of the CPU, and it also loads the kernel space. And I think people always, maybe not always, but often underestimate how many system calls programs are doing. Let's maybe do a little bit of demo. So I have a very simple program here. Let's guess how many system calls this program will do. It's just printing hello NDC TechTown. Who thinks it will do between 0 and 10 system calls? Raise your hand. Okay, we have 1 hand, 2 hands. Huh?
Counting startup code?
Yes. I will just do the strace, and this will be my command, because strace is a command in Linux which can measure the system calls, which will show you the system call done by the process. I will do the strace, then this program, and we'll see how many system calls it does. Okay, who thinks it's between 10 and 50? Okay, a little bit more, and who thinks it's more than 50? Okay, I think. Okay, let's try it. So I compile it, and then I use the strace like this, and it will show me all the system calls that my program's doing, which is quite a lot. I can count it by strace wc-l, so it's 37 calls. And if we look at this, a lot of those calls are just about setting the process. It's about setting the memory. For example, xcv is how we start executing. Then we have mmap. Then we have a lot of mmaps. Mmaps are setting the memory for the process. And just at the very end, we have a write command, which is our printf, which prints to the console. So yeah, 37. So switching. So a simple program can make a lot of system calls, and switching between user mode and kernel mode is not cheap, because you need to reload a new memory and switch the mode of the CPU. So usually you try to minimize the number of system calls you do. So on 32-bit system, when we have 4 gigabytes, this split looks like this. So on Linux, we have 3 gigabytes for user space and 1 gigabyte for kernel space. On Windows, it's usually half. So 2 gigabytes for the kernel and 2 gigabytes for user mode. And those are just the default, so they can be configured. On Windows, you can configure by some flag when booting the Windows, I believe. So you can always also achieve this 3:1 split. On 64-bit systems, we have split in just a half. So 128 terabytes for kernel and 128 terabytes for user space, both for Linux and Windows. Okay, so important question is, why are we mapping the kernel and user into the same other space? Cannot we just split them? Like, what is the benefit? And the benefit are performance reasons. It's cheaper a mode switch, and by mode switch it means kernel and user mode switch. It's cheaper the context switch, because the kernel can state mapped. So if we are switching between the processes and each process holds the kernel in the same space, which is not entirely true on modern operating system, but it's just idea, then the kernel can stay mapped. So it's cheaper. And it's less trashing TLB. TLB is part of your hardware that translates the virtual memory addresses into the physical memory addresses. It is just a cache. But important point for me was that it's not set in stone. You don't need to have kernel and user mode in the same space. And actually, there was a user and kernel separation in Linux. There was a patch in 2003, which was never merged, but there were a couple of distros using it, and it was totally separating kernel and user space into 2 distinct user namespaces, other spaces. So then the kernel had 4 gigabytes for itself, and then the user space had 4 gigabytes as well. How does it work on modern Linux? So we still have everything in one user space. But for security reasons, it's not entire kernel that is always mapped. It actually looks more like this. This is a solution called Linux KPTI, which stands for kernel page table isolation. And in kernel mode, we have what we had before. We had entire kernel mapped and entire user space. But when we switch to the user mode, which is when the program is executing, then we only have a very minimum subset of kernel being mapped into the memory. This is done for the security reasons. And this kernel space is also randomized, so it's not always into the same location. And it contains minimum amount of functions which are required for a full switch to kernel mode. So like entry-exit functions. It does it by having a separate page table. So it's still one address space, but there are two separate page tables describing those address space. One page table is complete. It has full information for kernel mode. And one page table has only this minimum subset of kernel. It provides some isolation between user space and kernel space. And it turns out it's a very good measure against the meltdown vulnerability. It was introduced before the meltdown, but back then I think it was optional. Now after meltdown, it's turned on Linux by default. There's cost to it, because it degrades the performance. You have two page tables, so every time you switch between user mode and kernel mode, you need to switch the page tables, which has a cost. So if you are running Linux in some isolated environment and you are not afraid of attacks, you are using it for scientific computing, I guess you can turn off the flag and maybe get 10, 20%, depending on how many and how frequent your application is making the system calls. It was previously known as a Kaiser. And yeah, here are some articles if you want to read about it more. Okay, enough theory, let's do some programming. So this is my setup. I'm using x86 architecture and 6.8 kernel. And how can we inspect the memory layout of process in Linux? Well, on Linux there's a great tool called pmap. And if I do man pmap, it will show me pmap report memory map of a process. So it sounds like exactly something we need. Description says the pmap command reports the memory map of process or processes. So let's go back to our simple example. We just have hello NDC TechTown. And I only put get char so my process doesn't exit immediately. So I can actually attach to it. Then, if I run it, I pass the PID of this process to pmap. I will get output like this. And there's a lot of output. Basically what happens here that each row is a single segment in the memory, which has its address on the left side. This is where it starts. And then if we want to know where it ends, we need to look at the size. The size is in the kilobytes. So then we can calculate where the segment starts and when it ends. For now, let's not look into this. Let's focus on the addresses here. Here are addresses of the sections. What will happen if I run this program again? Will I get the same addresses or different? Who thinks I will get the same addresses? Raise your hand. Okay. No one, okay. Who thinks I will get different addresses if I run this program again? Okay. Okay, I guess that was easy. So yeah, let's try. First time I get such addresses, second time, and third time. So those addresses are different, apart from the first one. But all of them are randomized each time. Why this is happening? And there's a mechanism called address space layout randomization, ASLR, and it increases security of binaries in process by randomizing position of some regions. And it also, in some places, randomizes offset between the start of some segments. On Linux, it's controlled by the randomized VA space file, which has three settings. It can be disabled. There can be conservative randomization, that's how it's officially called. And there can be full randomization, which is the default. And I can actually test on my machine if I do randomize. Let's display it. Okay, so the value now is 2. So it's default. It's turned on by default. But what I can do, if I set it to 0, and then I try to run the pmap. Okay, I think I have removed the get char, so now it exits immediately. Let me recompile. Yeah, so now if I keep running, I will get the same addresses because I disabled the feature. But if I enable it by setting it to 1 or 2, yeah, then the addresses will be different each time. The important point is that my binary must be compiled as position-independent executable, which means that it can be put anywhere in the memory. Because if I compile my binary with no pi, then it cannot be randomized, because then it expects to be loaded in very specific address. So if I would just compile it with no pi, then it wouldn't be randomized. Even if I had the randomize enabled, it would randomize all the other sections, but not my binary. Okay, let's go back to this listening. And if we look at those first two lines, we can see that those addresses here have different length. And before I said that the addresses are always 48 bits, right? So what is happening here? So the address at the bottom has 1, 2, 3, 4, 5, 8, 12, and each character encodes 4 bits, so it's 12 times 4, which is 48 bits. But this address at the top is actually 16. So 16 times 4 is 64 bits. So what is happening here? Okay, let's decode this address in the binary form. And now if we look at to the right 48 bits, those are the bits that are actually addressing. Those bits on the left part, those white bits, are not used for the addressing, they are just there. And the convention is that they must match the leading bit of the addressing part. So the register is still 64-bit, but only those bits participate in the addressing. So if I take this leading bit and I switch it to 0, then all the bits on the left side will also need to switch to 0. This is called canonical form of address. So while the address technically 64 bits, only 48 bits participate in addressing. And this most significant bit is used on Linux for distinguishing between the kernel space and user space. So in the user space, all the addresses start with this leading bit 0. So as a consequence, all the bits before must be 0. And in the kernel space, all the addresses must have leading bit 1. And if I look at the hex, it looks more like this. So the high addresses belong to the kernel. And they do seem like they are 64-bit, but only 48 bits are used for the addressing. If you want to read more about it, yeah, there's some link. Okay, let's look into this listening. There's a lot of sections here. First column is the address, so this is where the segments start. The second is the permissions. It's read, write, and sometimes it's X for executable. The P is for private mapping. It means we are not sharing this memory with other processes. Then we have the offset, which is only relevant if this section is mapping some file, because then it means which part of the file is mapped, starting from which offset. The inode is on Linux just the file ID. So by looking into the inode, we can know that those sections are mapped to the same file. Then we have size and RSS. Size is the size of the segment in bytes, and RSS is which part of those bytes are actually in the physical memory. Because sometimes segments are created with bigger size, but they are not using entire memory from the start, only partially. The anonymous means that in this segment is not mapped to any file, or it's no longer mapped to any file. For example, here we have libc, which is our standard library. We can see that the inode with this file ID is the same, so we're mapping the same file. And here we have some anonymous byte set. This just means that initially it was read from the file, but then it's no longer bound to the file. It's anonymous mapping. So whenever we modify the memory, it's no longer saved into the file back. Okay, so this is how the process looks like. It's not really clear what's happening, so let's start to unpack it piece by piece. Let's focus on our program. This is the program that I compile. I call that user program. And our program is mapped into the 5 parts. How can we understand which part of our program are there? We can use the readelf command, which will display the sections of program. So if I do readelf-s on my program, I get something like this. So those are all the sections that are in my binary. And some of them must be mapped, I guess, to the memory. How can we check which parts of them are mapped where? For that, we can use readelf-l to display the program headers. And it will give us information which sections are mapped where. And this is how the operating system also knows, because operating system looks into the binary, it reads those headers, and then it loads our executable. So if I execute this command, I see something like this. There's a lot of program headers, but the only important are those. The load program headers just tells the operating system to load the file, starting from some offset. And then there's a permission, so read, write, and then there's E for executable. Before that was X, now it's E for some reason. Whatever, it's just Linux. And then we have alignment. This alignment means that the section must be aligned to 0.1000, which is 4096 in the decimal, which is the size of the page. So it basically means please load those sections aligned to the page addresses. So we have 4 load instructions and 1 GNU rel raw instruction. The rel raw header means relocation read only, and what it does, it takes part of the segment and it switches the permission to read only. This is a safety feature because this is for making relocation read only, so no one is overwriting relocations. Relocations are used for dynamic linking. When you are using some functions from other binaries, you need to identify the addresses of those functions. So after the dynamic linker and loader loads those libraries, it marks the relocation segment as read-only, so no one can modify them. So now I can say, oh, this is the address of printf. So then when you are using printf, you are calling someone else's code. Okay, and how can we know which sections of the binary are used? We can either track it manually by looking the offset, and then if you go to previous slide, I can say, okay, so offset is here, so is this section, etc., which is quite tiresome. But I can also look here, because those are the segments of our file. Sections, actually, because segments are where it's in memory, sections is when it's in file. Those are the sections of our file which are loaded. So the first load instruction, which load those sections, the second load instruction will load this section, the third this, and the fourth, etc. And then the rel raw will make this part read only. And this part will be loaded here. So this part will be loaded here, and then those sections will be made read only. And if we look at this header load, the last one, we are creating it with read and write, which means that if we will, when we will make those as read only, we will split this segment. So we'll initially load one segment with read and write, and then we will mark some sections and read only, so we will split the segment. So we have 4 instructions of loading, but then we have 5 segments here, because one is splitted by this rel read only. There's a flag to disable it, so if you disable relocation read only, you only get 4 segments. So if I match those offset here and those permissions, because here I also have offset, then I know which segments are mapped where, and this looks more like this. Now I edited this file, so those are my notes. So in the first section we have interp. Which segments are important? In the first segment, I think the important is interp, which is the interpreter path, which stands for dynamic linker and loader path. This is the application that is loading your program. So when you have dynamic linking, when you use dynamic linking, then it's first the interpreter that starts with the dynamic loader, then it loads your entire file and it resolves the dependencies. And then it gives you control back to your program. Actually, I think if I have the binary here, I can read the section of readelf, for example, interp. Okay, something. Okay, interp. Let's try it again. readelf-x interp user program. And it will dump this section with interp. Here are the bytes, and here's the decoded version of LD Linux SO. So this is just the path to dynamic linker. In the next section, we have our code, which is in the text section, and we can see it by the permission. The permission is X for executable. And if I go back here, I can display this text section by using object dump, which will display all the executable section. And I just want to see, okay, here's this assembly of section text. This is our code. This is what we have compiled to. So if I scroll down, there should be our main function somewhere. Yeah, it starts here. Here are all the operations, and I can see the call to the printf and get char, which was in our main function. If we look at the segment higher, this is the raw data, which contains read-only data. So if I look in my program, I have literal char, the string. So this string is also, this literal characters is also read-only data. So if I do readelf raw data like this, then I can see that I have hello NDC TechTown in this binary at this position. And I can play it a little bit because this is read-only data. It's for all the read-only data, which are like const variables. So I can make const a, const int a equal to 089988888888, let's say, like this. And then if I compile it and I display the raw data again, yeah, I should have it somewhere here. Yeah. So we can modify the binary and we can see how it's reflected in the memory. The next segment is dynamic encode. This is used for the dynamic relocation and dynamic linking. It's out of the scope for this talk, but there are another good talks which explain this topic. I will link them at the end. And the last sector is in data and BSS. BSS contains uninitialized data, and data contains just global variables. So if I go back to my program and I declare some variable, let's say int a, and I don't make it const, let's say 0x77777777, and then if I compile it, redefinition, of course. Okay, so now I don't have const, so it should be in the data section. readelf-x data. So yeah, I have 7777. So it's here. Okay, if we try to visualize it, those section, first we have this is the process layout. First we have a random offset using ASLR equal to 1, and then we have those sections from the bottom of other space. So we will build it up gradually over this talk, and then we will compare it to my initial mental model and see how it differs. Okay, next section is heap. We know what is heap from C or C++. This is just some part of memory that we are getting the data when we are using dynamic allocation like malloc or new, right? So let's try to do malloc. And now I'm allocating 1 kilobyte of memory using malloc. And then I'm setting it to 0, because if you don't, the operating system is quite lazy. It will not commit the memory until it needs to. So I need to physically touch the memory to make the system do allocation for me. And let's observe this size of the heap. I will keep increasing the size of allocation. So I go to 10, and then it increases to 16. I go to 100, it increases to 100. I go 120, it increases to 124. And then I go further, and it suddenly shrinks. And somehow the other segment grows. Okay, what is happening here? So to understand this behavior, we need to realize that malloc has basically two ways to allocate memory on Linux. It obviously depends on the implementation of standard library, but it can either use the data segment heap, which it was using early, or it can make anonymous mmap. And mmap is just a Linux system call for mapping some file to memory, or just getting some piece of memory when you're using anonymous mmap. And the choice between those two methods depends on the mmap threshold parameter. It's documented here in the Linux map. So if I have this program and I modify it by adding this line malloc opt by raising the threshold to 200,000, and then I'm still doing 140 kilobytes allocation. I didn't change the rest of the program. Then I can see that the output will also change. So now I raise the threshold, so it's still using the heap. So it no longer uses the memory using the mmap. And I think the most important takeaway for me is that what we call a heap is not really a single region of memory. Heap is just something that standard library promises us to have. Or use the malloc, use the new, and then you will get some memory from the heap. But then it's up to the standard library implementation to actually get this memory from operating system and give it to us. So the standard library can use either the data segment or anonymous mapping. And there are trade-offs to both, because the heap segment can only grow in one direction, and then it can only shrink. So if you grow it a lot, and then you release memory at the bottom, you cannot shrink it, because you have still some data at the top. But when you are using the anonymous mapping, you can release them independently. You have like 10 anonymous mapping, you release some memory, you can give it back to the operating system. So this is just optimization. You can look to the STD standard library source code if you are more interested for that. Okay, so this heap is not really a heap, so I will call it not really a heap. And also in the computer science meaning, the heap is a tree-like data structure, and it's also not that, so I don't know why it's called heap. I guess naming is hard. So if we put this on our graph, first we have some random offset, but only for ASLR set to 2. If we have ASLR set to 1, then we have no offset at all. Yeah, and then we have this heap, which is not really a heap. It's more like data segment. Okay, let's move on further. Now I will jump to the top of the other space, and we have 3 segments: vSyscall, vDSO, and vvar. So there was a problem that switching between kernel and user mode was quite slow. And people who write Linux are very smart people, so they came up with a solution. Just don't require switch to kernel mode when you're using some system calls. And this is what those 3 sections are achieving. The vSyscall is just mapping, is just a segment from the kernel with those functions that you want to call quite often. For example, get time of the day. This is not a dangerous function to call to just get the time. So why require a switch to the kernel mode for getting time of the day? So this part of the kernel, which contains some frequently used function, which don't need to be protected by the kernel mode, has been mapped to the user space. That's why we can see it in the listing. So the user application can directly call this function without switching to the kernel mode. It has a couple of problems, because it's always mapped into the same location. That was the idea, so the program knows where to find those functions. But then the ASLR was introduced, and now this cannot be randomized, because all the program are expecting those functions to be exactly there. It's also a fixed size of the memory which is mapped, so it supports a limited number of syscalls, and it's actually been deprecated in favor of vDSO, but it's still mapped for the compatibility reasons. If you have some old program which relies on this, it needs to be mapped into your process space. So vDSO is the new solution. It's called virtually dynamically linked shared object. It's no longer a primitive mapping on some part of the kernel. It's shared library, so it can be ASLR'd. It can be moved randomly into the space. It's not frozen in API. You can add new functions to this. So it can accommodate more system calls than vSyscall. And the last object, vvar, is just the memory part used by the vDSO. It's just like its own heap. Here's some more info. So all those sections just serve to accelerate some system calls. That's all they do, by not requiring switch to the kernel mode. And if we put them in the graphic, then we have vSystem call, which is at fixed location, because it needs to be there. Then we have some random offset, and then we have vDSO and vvar. So this is how it looks in the memory. Okay, let's move into the stack. So first question, how big is the stack? I can check it by using ulimit-s, so the default size on my machine is 8 kilobytes. It can be changed, but within some limits, so you cannot set it to like 1 petabyte. There are limits in the Linux which you can set it to. And the very important question, which I was always wondering, why does the stack always grow downwards? Like, cannot it grow upwards? And the answer is, on x86, it always grows downwards. And what I needed to realize is that while heap is just a software feature, like your CPU doesn't know about the heap, your CPU doesn't know about the malloc, then the stack is both a hardware and a software feature. If we look into the Intel documentation, and we look into some instruction like the push, it says it decrements the stack pointer. Like your CPU does know about the stack. We have the hardware support for the stack in the CPU. We have the stack register, we have the dedicated instruction for manipulating the stack, and this documentation doesn't say decrement or increment the stack pointer. It tells about the direction. Pushing into the stack is always decrementing. Popping is always incrementing the stack pointer. Because I showed before that, for example, you can switch off ASLR. You can also disable kernel page type isolation, but you cannot, there's no magic flag in Linux that you can turn on to make the stack ground down upwards. It's just architecture defined. So my next question was, okay, so if it always grow downwards on x86, are there architectures when it grow upwards? And yeah, there are some. That's what Google told me. There's some Hewlett-Packard, PA risk, there's 8051, and in some mode on Spark it can also ground upwards. So the takeaway for me is that stack is both a software and hardware feature. Your CPU knows about the stack, but it doesn't know about the heap. So how can we inspect this, what is already in the stack? If we look at the size, we are just starting our application. Our application is very simple, and the stack is already being allocated 132 kilobytes, and it actually actively uses 16 kilobytes. So what is there? What are we using stack for? So when we have simple application, the stack is used for storing the local variables and also for storing the call stack. So if we call some function, we need to know where are we going to, where are we coming from. So I will debug this program. What I'm doing is I'm allocating one local variable, which should be stored on stack somewhere. Then I'm calling the bar, and bar calls the foo, and then I will put a breakpoint here. So how can I inspect the stack? I can use the GDB. So I just run this program in GDB, and then I just use the command stack. And this is more or less the output that I will get. On the left side, I will have addresses. So I have RB and RSP, which is the base pointer and the stack pointer. And then I can see what is earlier on the stack. So the top of the stack is here, and it grows downwards. So here I can see that I'm in the foo function, so I have return address to go to bar. Then I will be in the bar function here, and then I have return function to main. So this is what we have suspected. And then I have my local variable 999999 somewhere also on the stack. And before that, I have my argc and argv arguments. Argv is a pointer to the literal string, and then I have argc, which is just 1. So I can access those from the stack by just using argc and argv, right? This is all what we do. This is quite simple program. So if I print all the data from the stack, I will get something like this. If I user program 1, 2, 3, I will get argument 0, my name of my program, then 1, 2, and 3. And if I look into the stack, then I will see that my now argc is 4, because I have more arguments, and I still have pointer to pointer, which points to the beginning of the argv array. So if I visualize this, and this is the stack, I have my argc, I have my argv. Argv is a pointer, which points somewhere higher. Then I have array of pointers, which is argv 0, 1, 2, 3. And then higher, I have my literals. So I can transform it like this. And as you can see, I have a lot of free space here. So what is in this free space? What is already there on the stack? Like, for example, what is behind the argv? So let's modify our program. So I take the address of argv, and then I don't care about argc. I will just iterate, and I will print first 20 strings that I can find. And if I do it, I get something like this. I launch my program, I get 1, 2, 3. So I got my program, 1, 2, 3, and then I got some different things. What are those? Well, if they look familiar, those are environment variables. So behind my argv strings, I somehow get the NFP strings. And in fact, on Linux or on Unix-specific systems, you can write a function like this. So it takes a pointer to NFP array. So then you can directly print them. So on Unix system I can also take another argument, which will point something here, which will then point to the NFP strings. Okay, I have some free space here. What is there? There's array of some object which has type and value, and the type and value are 64 bits. So if I want to print them, because I check documentation, I already know their size, so I will call it a thing, and then this thing has 64 bit of type and 64 bits for value. Then I use the NFP pointer to iterate past over it. So I'm iterating while it's not null. And then I'm casting this pointer to thing, and I'm just printing this thing, printing the key and value, the type and value. And if I do it, if I iterate past the NFP, I will get output like this. I can see that some of the values look like pointers, some of the values don't. And keys are just numbers, they don't tell me anything. How can I make any sense of it? Well, this thing is called auxiliary vector. And I can actually set an environment variable, so the operating system will print it for me. So if I set environment variable ld show auxiliary vector equal 1, then the operating system will print it for me. And I can see that the values are the same. I was able to reach it just by reaching over the NFP. And then those numbers are decoded as some more meaningful names. But what are those values? Like, it still doesn't tell me a lot, right? I can run my program in GDB, and I can use the function info auxv, which will decode it and will tell me what it means. So for example, some are user IDs. There's also a number of program headers. There's system page size, which is 4096 bytes, which is 100 in hex. So why is it loaded into my program when I start it? So auxiliary vector is just meant to pass the information from the kernel space to user space. Initially, it was introduced to pass the information to the dynamic linker, the interpreter. But now it's more used just to pass any information from the kernel to application. So it's like preparing the space for the application, and if the application needs to know about the page size or something, it can get this information from auxiliary vector. And here you can read more about it. So so auxiliary vector is just behind the NFP. So I can put it on my chart that nvars and auxiliary vector is also on the stack when I start my application. And if I go to my chart, first I will have random offset if ASR is set to 1, and then I will have my stack. Okay, the last section looks like this. And what it is? It's so-called memory mapping segment. So before that, I said that there's a mmap function, mmap system call on Linux, and you use this to map some file to the memory part, or you can use it just to make anonymous mapping like this, like those three. So you just get a piece of memory. And this was also used by the libc to get memory for Heap. And this segment is just the pool of addresses that the mmap can use. That's why it's called memory mapping segment. So whenever you're using mmap, you will get some part of memory from this segment. It's also moved a little bit randomized by SLR, and then there's this segment. So this is pretty much how layout of my program looked like after we encoded everything. And if I compare it to my initial mental model, which was this, and now I have something like this. So I was close enough, I guess, but not really. Reality is a little bit more complex. But it's nothing super secret. You can easily in Linux just investigate it a little bit if you have a lot of time and understand what is happening. So this layout is quite big for a simple hello world. Can we minimize this layout further? So if we have a simple application, this was just a hello world, and it produced quite substantial layout in the memory. How can we minimize it? How can I simplify it? So one of the biggest parts that was taking the space was the memory mapping segment. How can I minimize the memory mapping segment? I can see I have the linker and I have the standard library. So let's start by getting rid of standard library. So to do that, I will compile with no stdlib, and then I need to change my program a little bit. I need to change my main function to be called -start, because this is the entry point on Linux. I could also pass another flag to the linker to say, hello, my entry point is the main function, so I don't need to rename it, but I can do this, just this. And if I do this no stdlib, then my memory layout will simplify a lot. I no longer have stdlib, I no longer have some to anonymous mapping, now I have only LD Linux. Okay, and the question to the audience, is this application statically linked or dynamically linked? Because yes? Yeah, dynamically linked, okay. So who thinks it's still dynamically linked? Raise your hands. Who thinks it's statically linked? No one, okay. So let's try, I think it was example 3. Yes, so I will no stdlib. I will just compile with no stdlib. Then like this, okay. Then pmap. Yes, I have this output, and then I ask LDD user program, and it will tell me statically linked. But if I ask file user program, it will tell me dynamically linked. So I don't think there's a consensus in Linux. Actually, this is dynamically linked because I still have interpreter section, and I'm still requiring interpreter to launch my application. It's just that LDD is using very unfortunate naming, because this is not statically linked. What LDD means is you loaded me, I'm looking into your dependencies, and you have nothing to load. I have no job to do, so I guess you must have linked everything statically. That's what LDD is saying. But technically, this binary is not static. Okay, but it gave me some idea. Now I can get rid of this guy by adding static. Now I can make my binary fully static. And if I do it, then my layout simplifies even further. So not only I don't have the interpreter and the stdlib, but also a lot of sections from my program has simplified, because those sections were serving for dynamic linking or for some relocations. And now I don't need them, so my program is much simpler. And if I compile with this program with static, and I ask LDD again, what it is now, it will say not a dynamic. So I think, so when it was dynamic, it was saying static. When it's static, it's saying not a dynamic. So it's very weird wording. The file will tell me that it's statically linked now, yes. Because I no longer has interpreter section, and I no longer require interpreter. Okay, can I minimize it even further? Well, we have the text section, which is our code. I guess we need to have it. But we have something like here, frame and frame. Those sections are used for stack unwinding, and some information for GDB. And there's one argument I can pass, no asynchronous unwind table. And then if I pass this argument, yeah, I will get rid of the section, and I have very minimum subset. Okay. There's one stack per program. But what about the multi-threaded programs? Because we know when we start the threads, we have stack per each thread, right? So I will have a program like this, just in C, and I have a thread function, will just print something, and I create thread like this, pthread create, and then I just join the thread. And if I do the pmap, I will have a little bit longer output, and those are new sections that have appeared. And the special care to those two sections, because this takes 8 kilobytes. And I know that the stack is usually 8 kilobytes, at least on my machine. And it turns out this is actually the stack. So it doesn't create another stack section here. It uses the memory mapping segment, so it uses mmap to create a block for the stack. And then just below this, I have a guard page, which is marked as read-only. This is to prevent the stack overflowing. So if my stack is growing downwards, and then if I touch the memory and I try to read something, it will segfault. This is just for safety feature. But if you are really smart, you can try to read past the guard page. You can like jump further, and then if you hit here, you can actually do it. So I guess it depends on your luck. And we also have some new segments here. Those are the segments used for the pthread support library, which it uses. What about more threads? If I create like 4 threads, what would happen then? Then I will have still only 1 segment for pthread library, but then I will have 4 segments here for the stacks. So I have thread 1, thread 2, thread 4, thread 3. And between them there's this guard page to make sure I don't overflow. So the takeaway, the stacks for a thread are just created by mmap. There's no extra stack segment. The mmap is used pretty much for everything. Okay, and the last but not least, how the just-in-time compilers can put the code into memory and execute it. Like when we think about Java, JavaScript, every dynamic language is interpreted, but it also just-in-time compiler. So it compiles it into the machine code and put it into somewhere in the memory and execute it. So let's try to do something like this. I will have a very simple function which adds 2 numbers. And I want to get a machine code for this function. So I just compile it, and then I use the object dump. Object dump will give me the assembler. This is the assembler for this function. And the machine code is here on the left side. So if I extract all the bytes, 55, 48, 89, 85, 89, 70, then this is my machine code. So in the theory, if I put this code somewhere into the memory, then if I'm able to jump to it, it should execute and add 2 numbers, right? Let's try to do it. So this is my program. And first, I'm allocating memory with using mmap. And the important part, I'm using protection exec to make that part of memory executable. Then, this is my code. Those are just the bytes I have copied from the previous slide, 55, 48, 89. So those are the bytes. This is the machine code for the add function. Then I copy those bytes to this memory that I have allocated before. And here I do the trick. I cast this memory into the pointer of function which takes 2 ints and it returns the int. And I need to be very precise with the function signature, because when we are calling the function, we need to put the arguments into the right place, into the registers. So, but as long as the signature of function agrees, then my C will think, okay, there must be a function somewhere, I guess. Then I just call the function like this and print the result, and it works. So this is how you can take the executable code, the machine code, put it into the memory, and execute it. Yeah, I think when I saw it, when I tried it the first time, I thought like it should work, but maybe it won't, and then actually did, and I was surprised myself. But I guess this is how it's done. And I'm not saying that this is exactly how the just-in-time compilers do it, but this is the idea. You need to obtain some memory, you need to mark it as executable, and then you can just jump it and execute it. There's a lot of stuff around it, like you need to align the stack, so you cannot just do a simple jump. But I use the C, so when I cast it to the int pointer to the function, it did all the alignment for me. Okay, some more articles to read, some more talks to watch, I recommend. And that was it. Thank you very much for your attention. We are in the time, and any questions?